welcome everybody to our second session of the advanced training for the South African Maths Olympiad. Thank you to the learners who are making an effort to come to these sessions, and hopefully you will really benefit by this, so that when you write your round 3, you will see the benefits of this. And I'd also like to thank the teachers that are here for attending, for encouraging your learners to go that extra mile with maths. That it's not just about school maths and marks, but there's a lot more to maths. And hopefully from the last session, session 1, you were all inspired to learn a lot more about mathematics. So it's a great privilege for me to introduce Dr. Jonathan Karev today. He is going to be our guest lecturer today, and he's going to teach you something about combinatorics. Over to you, Jonathan.
Hi, thanks Linda, and thank you everyone for coming, and congrats on making the 3rd round. That's a big deal. Well done. It's really nice to see this many of you. Yeah. Okay, so one more point. I did one of these things when I was in grade 11 or standard 9. I'm not sure what it was called then, and it was taken by Prof. Ridley. So if you don't like the format, blame him. So what's combinatorics? Combinatorics is a fancy way for saying counting things. And that doesn't mean 1, 2, 3, and now we're going to go up to 7 instead. We ask questions like, how many ways are there to choose 7 things from a set of 20? Okay, and another point I should make is I'm not really sure what level to pitch this at, so there's going to be a bit of auto-regulation here. So I'm going to ask problems and ask people to solve them, and at the point where they get harder to solve, I'll go into more details. Okay, so first question. So how many ways are there to choose 7 people from a class of 20 for a team? How many ways are there to choose 100 learners from 40,000 for the 3rd round? Yes, I know it's not quite random, but how many possible things could happen? These are questions we could reasonably ask. So, show of hands, who's seen this question before? Okay, so about half. Okay, so let's go into this. So first what we're going to do is we'll line up all n people. So first one. Up to the nth one. Okay? Now how many ways are there to do that? Well, there are n ways to choose the first guy, n-1 to choose the second guy, n-2 to choose the 3rd guy, so that's n times down to 1. Right? Okay, and now I'm going to draw a line after the kth person and choose all the people on the side. Okay, that makes sense, right? Now the trouble here is we can really move these guys around without affecting who's on the team or affecting who is in the 3rd round or whatever other thing we're choosing people for. Right? So we're going to divide this down to 1. And suddenly we can move these guys around however we like. Agree? Yes. Okay, and there are. Count one. Okay, now we don't really want to write dot 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 all the time. So we're going to use factorials, which really are just this. N factorial, written in exclamation point, is what this is. So okay, and the exclamation marks aren't n, they're n factorial, like this. And this is the formula for choosing n things from k. And n choose k is written like this. N choose k written like this is the number of ways to choose k things from n. Okay, so now something interesting about this formula, if you look at it, is that that's interesting. And you can see it's true from the formula. If you write n minus k and k, they just swap around. Okay, so why is that true? Actually, I have an answer here. Yes?
Because if you're choosing k people from a group of n, that's the same thing as choosing n minus k people to not be chosen.
Yes, very good. So, just to repeat that for the recording, if you choose n people to be on the team, say 100 people out of 30,000 to be in the third round, you automatically choose 29,900 to not be in the third round. Okay? So that's a very interesting thing. Okay, and here's another identity which is really interesting. By the way, I'm loosely following notes by Stefan Wagner from Stellenbosch University on combinatorics, which are designed exactly for this purpose. If you Google Stefan Wagner combinatorics Olympiad, you'll find these notes, and they're fantastic and they're really worth going through. So here's another. Okay. Okay, so let's talk a little bit about this object. Yeah? When n equals 1, well, this is 1 choose nothing. How many ways are there to choose 0 people from? How many ways are there to choose 0 people from a group of 1? Good, 1. And how many ways are there to choose 1? Also 1. Okay, you're in or you're out. And this is 2. Okay, if I'm going too slowly, shout at me. If I'm going too fast, shout at me. Okay, so how about 2? How many ways are there to choose 0 people from a group of 2? 1. And to choose 1 person? Yeah, it's 0 you. And to choose 2, just 1, and that's 4. How about 3? Okay, so none of you, cool, there's just 1. 1 of you, A, B, or C, they're 3. 2 of you, maybe it's a little harder, but yeah, it's 3 because of this idea, the one I just erased, but you choose someone to not be on the team and you're good. And finally, all 3, and that works out to 8. Is anyone noticing a pattern here? Yes.
Isn't this Pascali's triangle?
Yes. 1 sec. Yeah, so 2 to the power of n. Okay, so we spotted a pattern. Okay? Now, a fairly good strategy in Olympiads is to look for a pattern and then conjecture it and try and prove it. And sometimes you can go, well, I think this is true, I can't quite prove it, but I can prove it from this, and that's also going to get you some marks sometimes, depending on the examiners. Okay, so 2 to the n. Is there any... So let's try and prove that in general. Okay, does anyone know or see the proof? Okay, I'm going to take that as no. So here's the thing. We've got a team of some people that we're going to choose. And if you add up these numbers from 0, 1, 2, or 3, this is the number of teams we can make without any regard for how large the team is. So what this is going, you're in the team, you're not in the team, you're not, you are, and for every person we decide either in or not in the team, and multiply, the next one is in or not, and we multiply these through and we get to there. Okay? So that's a nice start with binomial coefficients. Let's just mention Pascal's triangle quick. So you saw this. So I left out 0, choose 0 as 1. There's one way to choose 0 people on a team of 0. There's these numbers we just add on. And I'm just going to write down another line. Anyone see a pattern? Okay, patterns are important. Yes?
To find a particular number, what you need to do is look at the two numbers directly
Yes.
above it and add them.
Very good, very good. So the pattern we notice here is that 1 plus 2 is 3,